So in essence, what you're going to be doing is what I demonstrated earlier, where you're going to be spinning this around. And a couple things. You want to make sure that the radius of the curve is relatively constant for a particular spin. So that means we want to make sure that this tape stays the same distance below the tube here. If I spin it really fast, that tape is now stuck in the tube, and yes, that maintains my radius, but now I have an additional force involved. So basically, all my data is invalid at this point if the tape is stuck in the tube like that. So I need to slow it down. If I go too slowly, this thing is going to fall, and so I need to get just the right speed. So the person spinning it, their arm is going to get tired, especially if they have difficulty nailing that right speed. So in theory, you can swap out, and you might have to swap out so you have a different person spinning it around, but it's not necessarily easy. Right now, I can't tell if it's level or whether I've got it going at some slant. But I'm willing to bet if all of us tried this, at least half of the people here, when they first start, will have the thing spinning around like this. You want it to spin as horizontally as possible. One of the things that has worked in the past for some people, sometimes it's just, oh, it's going at a slant, and then they can correct it. But sometimes try spinning it the other direction, and that has worked also. So, yeah, so you're going to be spinning it around for, I think it's 20 revolutions. If you've got multiple people in your group, all with a timer on your phone to the 100th of a second, not a 10th of a second, but 100th of a second, I have no problem with you getting 2 trials at this. Basically, one bit of swinging, 2 people doing timing, and count that as 2 times. I don't have a problem with that. Some issues in the past. I mentioned the broken string before. If the string breaks, then you still need to maintain the same radius. You're getting close to starting over if the string breaks. But also, if the string breaks, that mass is going to go flying across the room. Just please be aware of that. Occasionally check the string just to make sure it's not about to break. Some of these strings have been, I have actually no idea how long this has been in here, but it is rubbing against the edge of this tube here for quite a while. And so it's quite possible that, actually this string is looking pretty good, but they don't all look that good. I do recommend you using string if you're starting with a new piece of string. Use the string up there. Don't use the fishing line, because the fishing line will stretch and suddenly your radius has changed. The colored thicker string over there, this stuff right here, as you spin it around, will start to fray, will start to, I guess, spread out. And so you'll hear that, if you've ever had it's not as bad as the plastic bag in place of the hole in your car, but it will make an extra noise. You are bringing in air resistance into it, more air resistance with that string. So the white string over there probably works the best.
How are you measuring the radius?
All right, so before you start swinging it, you're going to have this set up so that this is a specific distance below the tube. I think I said 1 to 2 centimeters, so whatever that happens to be. And then the radius is going to be the distance from here to the center of mass of this.
Okay.
And you estimate what the center of mass is, basically the middle of the stopper. And so as long as this distance here stays constant, that distance will stay relatively constant.
And you would hold it like that?
To start with, and then once I get it going, I don't want to touch the string once I get it steady. I'm going to hold it a little bit just to get it going, but once I get it going, I'm only touching the tube.
Okay.
There was one semester where I had students holding it like this as they spun it around, in which case you can get that thing going as fast as you want. So the only thing that should be keeping this in place is that swinging.
Okay.
Please be aware as you swing it. You've seen me as I stop it, I sort of duck and I put my hand up. Whoever's swinging it, there's a good chance you're going to smack yourself in the back of the head. Be aware. The rubber stoppers are not metal discs, so it's not as bad as it used to be, which doesn't help you at all, but yeah, it's a rubber stopper. No one I don't think anyone's actually been hurt, it just sort of, it's not something you really wanna do.
Is revolutions terms, like, times it goes around?
Yes, yeah.
And that's what we're timing?
You're timing how long it takes to go around, I think it's 20 times.
20 times? Okay.
Now, if you have somebody who's getting going and they're very comfortable with it, you can do, it's not like you have to do 20, have them stop, write it down, then they start up again. If they're going comfortably, you can do 20, write it down while they're still swinging, and then start up again, so figure out when they're gonna start counting again and do it that way. So that they don't actually have to stop. They don't have to stop. If they want to stop, fine, but they don't have to stop. And then they might end up swinging it 150 times instead of 100 times, but once you get into a rhythm, it's sometimes helpful to just let it keep going.
But you said that if we have multiple timers, you can just do one trial.
Well, you won't have so many people in your group that you can get them all in one shot.
So the second chart is gonna be our calculation. The first one is what we're actually seeing, right?
Right, so the first one, too many variations of the lab. Thank you. So hanging mass is something that you'll measure. You got the 5-time trials for each different hanging mass. So yeah, table 1 is the stuff that you're measuring directly in the lab. Table 2 is the stuff that you're calculating. So once table 1's filled out, you have fulfilled what you have to do here.
Okay.
Right? Feel free to stick around, but at that point, you've done what you have to do.
Okay.
Ultimately, there's a graph. Yay. The tension, so the graph is like speed squared versus tension.
The centripetal force.
Centripetal force, which is the tension. Centripetal force. And that'll be in newtons, and then for speed squared versus that, is that right?
Yes.
I think somebody said yes.
Wait, hold up, I'm not seeing this. That is the linear speed squared?
Yeah, that's speed squared
Okay, okay.
with units of meters per second squared, which I can write this way, or I can write as meters squared per second squared, either one. I know that centripetal force is mv squared over r. R, you've measured, that's or L or R, I can't remember. Again, too many variations of the lab. Is it R or L? It would be at the top, one of those top 3 things. R, okay.
Yeah.
So you have R, which you'll know beforehand. You're not using the mass that you measure directly for the swinging mass. You won't use that till, I think, the last analysis question. So this is what you're gonna find experimentally, and then compare it to what you found by putting it on the triple beam balance. So you're gonna be plotting V squared versus the centripetal force. So I want to get this into y is equal to slope x plus b form, classic line. My x is my horizontal, but centripetal force, and y is my vertical, or speed squared. So I'm going to take this equation here, and I want to get v squared all by itself. So I'm going to multiply both sides by r. So I get r times fc is equal to mv squared. Then I'm going to divide by mass, because again, I want v squared all by itself, so I have to get rid of all the other stuff. So what I'm left with is v squared is equal to r over m times centripetal force plus 0. So what I would expect in an ideal world is that your intercept would be 0. Odds are against that, but we can pretend it's going to happen sometime. So that your intercept will be 0, that your slope is that r divided by m. And I believe I actually write that on there, where I tell you that the slope is r divided by m. This is where it comes from. I think analysis question number 4, 5? One of the ones on the second half of the page. 4, okay. The slope will have units. So if I ask you what the slope is, I do expect units. And I think with that, let's see if I counted correctly before, so we have 11 in here. I really don't want a group of 2. So if we had a group of 4, 4, and 3, I think that'll do it. All right, I think, any questions before we start?
So is the top half, this one up here,
Yep,
we're measuring the mass. with
yes.
the triple beam
You're-
balance.
So you use the triple beam balance to measure the mass of what you're swinging around. That's at the very top.
But this one, we're calculating the mass.
So,
Same thing?
so the mass of the stopper, the thing that's swinging around goes here, that's that mass. Hanging mass is what you're gonna be hanging underneath it. So you'll use triple beam balance to get an actual measurement, I believe, as opposed to trusting them. Let's see. Oh, it looks like I have you trusting them.
So just read what it says.
Yeah, that's no fun. The hanging mass down here is
Would it be the same
just the
this
same
one?
as that.
Okay. Okay.
Yeah.
You confused me, because I thought you said that we're not measuring the mass, and I was like, wait, how did we figure it out? Well, okay.
Yeah, so hanging mass is just write down what the hanging mass was from the top.
So hanging mass table 1, hanging mass table 2 are equal.
Yes, they are. They are just, it's the same 5 numbers or 6 numbers that,
Is it 5?
same 5 numbers.
Beautiful.
It's also possible, let's see, same units? Yep, kilograms, kilograms. Yeah, for some reason it made sense at the time. All right, 1 group of 3, 2 groups of 4, and let us rejoice because as you know, this is physics.
Can I borrow your stapler?
Pardon?
Hold on, your stapler.
Oh, yeah, absolutely.